Okay, so I will start with the slides that I have left in the last lecture. Now I will continue from the last slide, point that we were talking about. So the point was that when you have the conservation laws, when you have the conservation of mass or conservation of energy, conservation of momentum, in all of these laws, you have one thing that is very common, that it is very similar to, if you remember, we have talked about the as the map of Azerbaijan, and we have said that you are selecting the boundaries of Azerbaijan as your system boundary, and the people will be the system variable. And for the conserved quantities, we'll look for the change of people. If you remember that we have said that the change of people will be equal to the total people that are coming into Azerbaijan, traveling into Azerbaijan, and that one will be equal to the people that are leaving Azerbaijan, and you will have the birth, and you will have the death of the people. This one was for the general map of Azerbaijan. Also, we have talked about when you have the money. So we were talking about the money have changed. And the last point was we talked about the conservation of the energy for an open system. We have said that for conservation of energy for an open system is that you may have the heat transfer out of the system. You may have work transfer into the system. You may have the work transfer out of the system. It is a possible one. And you also may have the heat transfer into the system. When we say the Q, it is heat transfer. Okay. When we say W, it is the work transfer. Okay. So these were the two types of the transfers that are common for any system. And the work transfer, it can be that the example can be electricity, for example. If you have the electricity cable that crosses the boundary of the system, then you will have the work transfer. Or you could have the shaft work. Shaft work means that there is some system that crosses the boundary, there is some shaft that crosses the boundary of your system, and that shaft, this one rotates, okay? And since this one rotates, you will have the shaft work that crosses the boundary of the system. And this one was for the any system, and as well as if you have the mass, if there is fleet, that then is the fleet. If the fleet crosses the boundary of the system, and also fleet leaves the boundary of the system, this one will be the outlet, and that one will be the fleet inlet. Okay, and then for this one also, the fleet will carry with some mass with itself. So I can show the mass as m here. For the outlet also, I will show the mass outlet, mass inlet. Okay, and during this process, there will be some heat transfer, there will be some mass transfer, and there will be some work transfer in that system. And then during this transfer processes, you will have change of the system energy. Okay, the system energy will change. So as a result of this one, let me write as the general equation here, so that change of the system energy, system I mean whatever that is inside these boundaries. We have the boundaries here, that will be the change of system energy. That one will be equal to the total inlet to the system minus total outlet to the system of the system. And for the total inlet, you will have the mass that crosses the boundary of the system. This mass can carry with itself the internal energy. It can carry with itself the kinetic energy, for example. It can carry with itself, for example, potential energy, okay? Or it can carry with itself the pressure energy, okay? We'll talk about these ones in our open system analysis, but for general analysis, this will be true. And it can bring also the heat transfer into the system. This one can bring the work transfer into the system, and the minus, the mass transfer out of the system. Again, it can take internal energy with itself. It can take the kinetic energy with itself, potential energy with itself, and the pressure energy with itself. Okay. For outlet, there can also be the heat transfer. There can also be the work transfer. These are the transfer quantities that will be valid for the system here. And also the change of the system, this one will be, system will consist of the system energy. System energy will be internal energy, which we show as U, and the kinetic energy and the potential energy. Okay, this one is the internal energy. I will talk about what internal energy is. And this one can be the kinetic energy, and then mv squared by 2, and the potential energy mgz. Okay, so during this process, so there are some inlets, some outlets. Okay, there are some heat, work crosses the boundary, fluid leaves, fluid enters to the system, and during the process, the inside of the system, there will be change. For example, its internal energy can change, its kinetic energy can change. For example, this system can move with some speed, its potential energy can change. Okay. But I will show, I will give you some the simplifications. This term becomes 0 so if it is closed system. If closed system, then there will be no mass transfer and there will be no, so this term is also 0 for closed system. This one is 0. And then, so in most of thermodynamic devices, we are not considering this kinetic energy and potential energy here. So for most thermodynamic devices, okay, for most thermodynamic devices, this kinetic energy and the potential energy terms are 0. Therefore, whatever left is that heat transfer minus work transfer. This will be the general condition for any thermodynamic device that we are doing an analysis. So the last result that is very important will be that change of internal energy of a system will be equal to Q in plus work in minus Q out plus work out. This will be the case that we will look for. And when we say the internal energy here, U means internal energy. So internal energy means the sum of molecular energy of the system. So the molecular energy, for example, molecules are moving in random directions. During that motion, they can have translational motion because molecule moves from one point to another point. Therefore, it will have the translational motion. Molecules can also vibrate, and they will have the vibrational energy. Or rotate, they will have the rotational energy. If there are nuclear reactions, molecules can have nuclear energy. Therefore, different types of energies, but we are talking about at the molecular level. Different types of the energies at the molecular level, they are exposing themselves as a result as an internal energy. Okay. At the lowest scale, it is molecular energy, but some of this molecular energy becomes macroscopic, and that macroscopic energy is called internal energy. It is the manifestation of the molecular energy of the system. So this will be the general case for the molecules. And now I'm going to apply this equation that delta U system Q in plus work in minus Q out plus work out. This is for the open systems. Let me add this one. This one for open systems. But for the general equation, this is the general one, okay? This one is general. When I mean general, you have the kinetic energy of the system, potential energy of the system, internal energy of the system will be equal to mass transfers and minus heat transfers and the work transfers. Now I will apply this general equation, this general one, to some systems, thermodynamic systems, and then I will do some real-world example. The first system will be this one. So I will apply that equation to this system. So firstly, let's understand what is that system. Here we have the water here, cold water. If you have seen, this is from our mechanical engineering lab, so fluid mechanics lab, and that also heat transfer lab. So this is the cold water here. This cold water, it circulates in our system, okay? Since it's heavy because it is cold, it moves down these tubes here. Moves down here, moves down here. So you can see there are lots of tubes here. The cold water moves down, and there is the sun energy that falls onto that system. You have the sun energy. Okay, these are, let's say, assume that the sun energy. When sun energy falls on that system, this cold water, these are cold. It becomes hot, and then rises these tubes up. So it becomes hot. So all of it becomes hot. And hot water rises, and the cold water, this is very high school knowledge that you know it, cold water sinks. Okay, and why hot water rises? Because that is the densest stuff that you know it. It has a low density, but the cold water has the high density. So rho high. Since this one has a low density, this one has a high density, and here you will have the exchange of the mass. And this hot water will come back to this cold water tank here. At the tank here. This will go back to the cold water tank, and we will have the mixing process, and after some time, this cold water tank will be hot, and you will have the equilibrium conditions, and there will be no heating at all. This is the general picture, and now I will apply this equation here that says that the change of system energy will be equal to in minus out. And for the case now, I will select my system or the control volume. So that select control volume. When I say that control volume, it means that open system. Okay. When I say that, so that when we say that system, so when we say system, generally system, it means that it is closed. But when we say that the control volume, it means that it is open. Control volume. If you should remember these terms from our previous lectures. Okay, so this will be that. The control volume now, I will select the control volume as this, the tubes here. This will be my control volume. So that my control volume CV will be tubes. These tubes are my control volume. Now I will apply this general equation for that tube system. I will have the change of the energy of the tube, so that delta U of the tubes, and we don't consider the kinetic energy of the tubes because you can see the kinetic energy of the tubes are zero. The tubes do not move up and do not move down. They are at the same position. And also potential energy of the tubes is zero. Therefore, we only have this delta U tubes, which is this system, left-hand side. Okay. And then you will have the into the system will be mass in with kinetic energy, internal energy, and the potential energy, and then this the pressure energy. So you will have the mass into the system. It will consist of the internal energy. It will consist of the pressure. It will consist of the kinetic energy, because the fluid that comes into the system, it will bring some kinetic energy with itself, and the Gz, which is the potential energy. You see, this is open system. And then from this open system, you will have the Q in, because sun energy is the Q in. If you say that the sun energy, that is Q in. And then I will have the work in term, which will be 0. If you see that work in, there is no any work into the system. You can see there is no any rotating shaft. There is no any electricity. Therefore, this system will have no work transfer, and therefore work transfer part will be 0. Okay, very simple stuff, and the work transfer part will be equal to 0. Now let me add that term here so that you can see. So plus work in term, that will be 0, because as I said, work in means something that rotates, for example, shaft, or the electricity. The famous one is electricity. There is no electricity. And then comes the mass out. There will be mass out from the system. It will carry some internal energy. It will carry some potential pressure. It will carry some potential energy, and it will carry some the potential energy and the kinetic energy. This one will be for the mass that leaves the system, because, as I said, cold water comes in the system and the hot water leaves the system. And the plus Q out term will be 0. There is no Q out from the system. The system gets heat from the sun, and the work out, as always, is 0. Okay. Now we can do even some more simplifications here. Additional, let's say, simplifications. We can do that. It is possible because the engineering means that approximations. Okay. So that what will be your approximations? Firstly, you can argue that the pressure that comes into the system, the pressure that leaves the system, is almost atmospheric pressure. So P in cold water is approximately the same as P out hot, and it is approximately 1 atm. Yes, it is true that hot water has higher pressure. It is true, it is more than the cold water, but you know that in this type of systems, pressure doesn't play a great role. Okay, therefore the pressure term is 0, and also kinetic energy, velocity in, is approximately the same as velocity out. We don't have a large amount in change in kinetic energy. So when I say that these terms are 0, I mean that these terms are 0 with respect to the main term that you will see. It is very important. And also the potential energy is approximately the same as potential energy out. You see, with these approximations, you can even neglect terms here, and you will have only internal energy. So why internal energy is the main player here, as well as this Q in? It is the important part, because this internal energy that lives into the system is proportional to temperature. Okay. And these type of systems are having temperature change, more temperature change than the pressure change. Okay. Therefore, this one is also proportional to temperature. Okay, proportional. This sign means, let me add it here. This sign, see this interesting sign means it is proportional. It is proportional to temperature, and this one is proportional to temperature inlet, temperature outlet. Therefore, you can see that this internal energy is important. So as a result, you will have this equation where it says that the change of internal energy of the system of the tubes will be equal to the mass transfer by some internal energy, mass transfer by some out internal energy, and the plus the Q in term here. If you have questions till now, you can write in our chat. If you don't have any questions, I will move on to next example here. If you have questions, you can ask. It seems that nobody has questions, so that I will move on to next device here. What we are doing is that it is not a mathematical stuff. We are just applying this first law of thermodynamics on the devices. Now I will have, so first let's solve one example here. Then from that example on, we can move on to the next applications of the thermodynamics. The example says that we have a rigid So the example says that we have a well-rigid insulated tank contains 2 kilograms of air with a volume of 0.6 meters cube. This is the rigid well-insulated tank. And let me firstly use these keywords here that will help us to simplify the problem. When we say that insulated, you should remember this from the previous lectures, that insulated means that Q is 0. Okay. You are adding some insulation materials, and then you will have this Q term is 0. And it contains 2 kilograms of air, and the mass is 2 kilograms. And with a volume of 0.6 meters cube, volume of 0.6 meters cube. There is a paddle wheel that transfers energy to the air at a constant rate of 8 watts for 10 minutes. What it means is that I have a container, something like this one. And the volume of the container is given, which is 0.6 meters cube, and the mass of the air. So this one is very important. Air is the 2 kilograms. And also it says that there is a paddle wheel. The paddle wheel is something like this one. Okay, let me add the 3 blades here so that it doesn't look like. So paddle wheel is something that rotates. But this one rotates, okay, and it is connected to some shaft here. Okay. This one rotates with some speed of omega, and during that rotation, it gives some energy into the system. You can see it rotates. This is the shaft, and this one is paddle wheel. It is very similar to where is the paddle wheel? It is, you can say that paddle wheel is fan. Okay, the fan rotates, the blades of the fan rotate, and with a power of 8 watts and for 10 minutes. If the kinetic and potential energies of the air are negligible, so do not consider the kinetic and the potential energy, it says, then find the specific volume at the final state. This is the first step. The transferred energy is in kilojoules. The change in the specific internal energy of the air. This is a very startup example for the fluid thermodynamics one. So it gives understanding what's going on in thermodynamics. So let's start. Firstly, the question specifies that find the specific volume at the final state. And if you remember the specific volume is the volume per mass. And this one is exactly 1 by rho, density. Okay, when we say density, it is mass per volume. And when we say specific volume, it means that the volume per unit mass. Okay, now let's find it. So it says that at the final state, okay, final state, if you look at the final state, firstly, I should select my system here. So if you look at my system, this one is the rigid system. For the rigid system, volume doesn't change, it is constant. And as well as my system is closed, since it is closed, the mass is constant. Okay, this one is closed system. There is no in and outlet, and there is no change in volume because it is a rigid body. Volume is constant. Therefore, mass at the initial process, which is 2 kilograms, is constant. Volume is constant. You just divide these two ratios. 0.6 divided by the 2, you will have the 0.3 meter cubes per kilogram. This is the first case. And now comes the A case, we finished. B case, transferred energies in kilojoules. Firstly, we should look at the transferred energies here. So firstly, how many types of energy do we have for the transfer? Transfer can happen by mass, energy transfer, let me add it here, energy transfer. There are 3 types of energy transfer. One can be by mass, the one can be by heat, and the one can be by work. Okay. Only 3 types of the energy transfers here. One can be by mass, and the one can be by work, and the one can be by the one can be by the heat, work, and the mass. So the question says that it is closed system, therefore no need to consider the mass part. This one is 0, closed. And the heat transfer is 0 because we have said it is insulated. There is only work transfer, okay? And this work transfer is by paddle wheel. And for the paddle wheel, it is work done on the system. There is work done on the air. Okay? Because this paddle wheel does work on the air. Okay? It does work on our system or on the air. Therefore, it is work in. Or easy way to understand this one is that, or you can say that the fan or paddle wheel, this one needs electricity. The paddle wheel needs electricity, and since it needs electricity, it will be work in. Okay? It needs electricity, or it needs some electric power, therefore it is working. That's all. But this is the simplest way to understand whether it is work in or work out. And to find the energy for paddle wheel, it will be that 8 watts, this one, multiplied with the 10 minutes, multiplied with the 60 seconds. And overall, it will be that 4800 or 4.8 kilojoules. Okay, this is the work transfer to the system. Now the last part says that the change in internal energy, specific internal energy of the air. Let's do that. For the last part, I will rewrite the first law of the thermodynamics. The first law of thermodynamics, if you remember, it says that change of energy of the system. So this one is, for our case, it is air. So the air is inside this tank. The change of the system energy of the air will be equal to the total in, which is the mass in. It can bring the internal energy, it can bring potential pressure energy, it can bring the kinetic energy, it can bring the potential energy, plus the Q in term, plus work in term. This one will be the in terms. For out ones, you will have the same terms here, and the Q out, and the work out. And we have specified that our system is closed. Therefore, the mass term parts is 0. This one is 0. That one is 0 because it is closed system. Heat transfers are 0 because it is insulated. And the work transfer parts are 0 for outlet because this is paddle wheel. So there should be one more bracket here. We are just adding it. There will not be any work transfer out of the system, and we will have only that work transfer which is into the system. And in the question, it has given us the 4.8 kilojoules, 4.8 kilojoules. And therefore, for the change of energy of the system, we have said it will be a change of internal energy, it will be a change of kinetic energy, and it will be a change of potential energy. And we have said in previous slides that these two terms, most of the time, are not considered for thermodynamics, 0. And even in the question, it says that even if neglect kinetic and the potential energies of the air. You can see the question itself says. Therefore, the change of air internal energy inside the tank, so air inside tank, will be equal to 4.8 kilojoules. This one is internal energy, but the question is required for the specific internal energy. And when we say that specific internal energy, you just divide by mass. So delta U divided by air divided by mass, it will be that specific internal energy. And the mass is 2 kilograms here. It will be that 2.4 kilojoules per kilogram. Okay. When we say specific, it is per unit mass. And with this one, we have finished this example. Now I will move one more example I will do one more example, but before moving on the example, I want to see the number of the participants here so that I can take the list for the participants. So let me take the attendance. Okay. So next example. The example is, we have the piston cylinder device. You can see it here, it is given. It goes a process where specific internal energy of air decreases from 2709.9 kilojoules per kilogram to 2659.6 kilojoules per kilogram. So during the process, the internal energy of the air drops. Heat transfer to the system is 80 kilojoules. Paddle wheel work is 18.5. You can see the paddle wheel here. You can see it is fan. The paddle wheel rotates and it brings a negative quantity here. I will talk about what negative means. And the Q is 80 kilojoules. And you can neglect the kinetic and the potential energy of the system. If you do that, if you neglect it, the kinetic energy, if you neglect the potential energy, and then you will have only the internal energy change of the system. So the question says that determine amount of energy that is transferred to the system and then show the units in kilojoules. Okay. Let's do our example. And we will again start with the application of the first law of thermodynamics. And the first law of thermodynamics says that, let me write it. It states that, choose a color here. It says that the change of the system energy will be equal to the mass into the system. So I will not write all of the quantities here. I will just write the mass, and it will, let me write it, because at the end you will memorize the equation here. It is not so difficult equation. It will be kinetic energy per potential energy and the pressure energy, and then you will have the kinetic, potential, and pressure, and the internal energy. This one plus Q in plus work in minus, similarly here, mass out. I will not write all of the equations here, and the minus Q out and the minus work out. Okay. And the change of, first let's identify our system. What do we mean by system? Here you can see the dashed lines. You can see the dashed lines. It only consists of the steam. Okay. Therefore, our system is steam. Okay. And to our system of the steam, there is paddle wheel, there is heat, and during those motion, during those transfers, we have also the motion of the piston here. You can see it moves, and during those processes, the system energy or the steam in energy change. It can change, as I've stated, always as a internal energy. It can change as a potential energy, a kinetic energy. It can change as a potential energy. And as well as the question states, and I've said it, in most of the thermodynamic devices, we don't consider this part. This part is 0, and only remaining term is internal energy change of the steam. Since this one is closed, therefore this term is 0, this term is 0, closed. And you see there is a negative sign used here. I will talk about what negative sign means. So when I say that Q in, okay, I say 5 kilojoules. Okay. So you see that I have specified the in quantity, which is 5 kilojoules. Or instead, I can write this one as Q is 5 kilojoules. It is the same. But when I say that Q out, or heat transfer that leaves the system, Q out means heat leaves. So Q out 8 kilojoules, or I can say that Q is negative 8 kilojoules. You can see here. So instead of specifying in and out terms, I use the signs. If the sign is positive, it means that it is in. If the sign is negative, it means that it is out. This is one. For the work term, it will be the opposite. When I say that work in, it is, for example, 4 kilojoules, or I can write this one as the work is negative 4 kilojoules. See, this is the same. So I can specify the in term here by in means that it uses electricity. Or I can say that work out, and it will be that negative. It uses electricity, or this one can be that work done on the system. This one is very important. Work done on the system. And the work out, when I say that work out is that 6, for example, kilojoules, or I can say that work is 6 kilojoules. See, so I can specify the in and the out terms. Work out means that done by the system. I can specify if it is out with the out subscript here, or I can just write work is 6 kilojoules. Doesn't matter, it is the same thing, but two different notations. This one is historical, this one is new. Now let's go back to our question here. It says that the heat transfer to the system is 8 kilojoules. You see it is positive, then we are talking about this one. So I will write this one as Q in is 8 kilojoules. And the paddle wheel work is negative 18.5 kilojoules, and it means that negative means work in. So I will write this one as work in is 18.5 kilojoules. You see, I don't use the sign again. Okay, if you use the sign again, you will be in trouble. So instead of that using sign again, you just add the in here. I just add in, which is 18.5 kilojoules. Determine the amount of energy transferred from the system. Okay, let me first add these values here. So that it says that specific internal energy of air decreases from this one to that one. This is not actually air, this is steam. Specific internal energy of the steam decreases from that term to this one. Let's first write the delta U here. Delta U will be that 2659.6 minus delta U. When I say delta U, it is U2 minus U1. And this one minus the U1, which is 2709.9. This one is kilojoules per kilogram. And I should multiply with the mass term here, which is 5 kilograms. And therefore, you will have the kilojoule term here. If you do these calculations, you will get, let me do that for you, 25. If you have the answers, you can tell me your answer. Let me see the chats. So I can wait for your answer. Actually, it can be better for me to see your answer. What do you get from this term here? So you can write your answer as a comment. So I can write your answer. You can write the answer as a comment so I can see it. It means that we are working together. So yes, there is one answer from Reza. And Reza says it is negative. Yes, it's possible. The negative means that it decreased. Negative 2. Reza says that 5, 1 point. Let me see the Reza's answer here. 5.5. Yes. It's 5 kilojoules. So I have found the left-hand side, which is this one. This one is negative 251.5 kilojoules. And I have Q in, which is 80. And I don't have Q out, which is 0. I have work in, which is the 18.5, 18.5, okay. And the left-hand side is negative 2, 5, 1. Let me write it here, the final equation. It says that negative 2, 5, 1.5 will be equal to 8 plus 18.5, okay. So I have one unknown, which is the work of the piston, okay. And by the way, I don't know whether it is in or out, okay. So I can write this one as I don't know whether it is work in, I don't know whether it is work out, but from the combination of this equation, I see that it should be work out, because this term is this term should be smaller to get the negative quantity here. Therefore, I write work out and the piston. You can see it. So that determine amount of energy transferred from the system to the piston. It will be work out, and therefore work out will be this quantity here. And if you have questions, you can ask. If you don't have any question, I will wait for your answer again for this part. And again, I will finish this example. Then I will do one more example if you have time left. So let's see what's your answer here. Let's see your answer. What do you get work out by piston? There is one answer. Okay, good. It is 349,345. Okay, so that the answer is 350 kilojoules. Okay, this is the answer for the question. You can see that the questions are very easy. You just have one equation and one example, so you can solve it. I hope there is one more example here. Let me see that example too. Yes. We have a piston cylinder device that contains a fluid that passes through 4 processes, and the system completes 80 cycles per minute. The sum of all heat transfers is 80 kilojoules. Complete the given table and find the network output in kilowatts. Determine whether it is property out of the system or into the system. This is a very complex and good question that with this one we'll finish our lecture. Let's do it and solve the question. We have the piston cylinder device, and there are 4 processes. Okay, and these 4 processes makes a cycle. So these 4 processes are parts of cycle. Parts of cycle, it means that I start at some point here, or for pressure value, for volume value, for the temperature value, and the system does some work. It does some work and go back to the same point, so that initial and the final are the same. Okay, initial and the final points are the same, and this is the cycle. Okay, that is the meaning of the cycle. You have started from some point, and I can give one example for the cycle is the refrigerator. Okay. For example, refrigerator is a cycle, or car engine, it is a cycle. Okay, these are the examples of the cycles. You start with some point that is given at the beginning of the process, or I can show it with a PV diagram. For example, the pressure versus volume, And for PV diagram, for example, this one increases, you go first way, and then drops, you go that way, and then drops again, and then increases again. So you can see this is again cycle. The arrows show the direction of it. This one is, for example, 1, this one is 2, and this one is the 3, and this one is the 4. So the pressure volume changes in that manner, then it drops, and then it drops again, and then increases one more time. This is one cycle. You see that the point 1 where you have started is the same as where you have ended. So with the first 1, 2 process, I will apply for each process the first law of the thermodynamics. First law of thermodynamics says that the change of in system energy. So I not want to state it again and again, iterate this term that the kinetic and potential energies are neglected. I will just write this one as delta U. And also the mass terms are zero because this is again a closed system. So this piston cylinder device, it is closed. It is very similar to this system here. You can see that the system is closed. There is no inlet and outlet. For example, that the refrigerator, okay, refrigerator is a closed system. After some time, there can be leakage, and therefore you are adding some gas to your refrigerator. But if there is no leakage, the refrigerator is a perfect closed system, and therefore you don't consider the mass. And there will be only two quantities, which will be that Q in plus work in minus Q out plus work out. During the first 1-2 process, Q is 0, so that, let me add it. Q is 0, Q out is 0. And the work quantity, you can see it is positive. You see, the in and out is not shown here, but the sign is shown. If I go back to here, when the work is positive, you see, when the work is positive, I mean it is work out. Therefore, I will write it as work in is 0, and the work out is 2500 kilojoules per minute. See? So therefore, the change in delta U will be equal to negative 2500 kilojoules per minute. I'll just write it here, negative 2500, and the unit is also kilojoules per minute. Okay. This is the first process, and I will apply the second process. That means different color here so that you don't mix up the processes. Delta U will be equal to again Q in plus work in minus Q out plus work out. And for the process, let me add the processes here so that this one is 1, 2, and the second one is the 2 and the 3. For the 2, 3 processes, Q is positive. You see, the sign is positive. I'll go back to the here. When Q is positive sign, it means in. So therefore, the in part is 20,000 kilojoules per minute. And the work part is 0, therefore I put 0 here, and I put 0 here. There is no Q out, 0 here. And therefore, delta U for the 2, the 3 process, it becomes 20,000, again positive here, 20,000 kilojoules per minute. Now comes the 3 to 4 process, and I will use one more color here so that you see a colorful screen here, so that you will have again the delta U will be equal to Q in plus work in minus Q out plus work out. And for the 3 to 4 process, you can see Q is negative. You can see the sign here. You are very, yes, you can see the negative sign here. When I say that the Q is negative, so I mean the second one, which is out quantity. Therefore, I just add the Q out, which is 3000. You see, I don't play with the units here again. Okay. When I say that positive and so sorry, the sign here, because when I say that Q out, it should be always positive. But when I say negative Q, it means that it is out. And the work term, should be determined, and the delta U or delta E, this one is delta U, actually it doesn't matter. This one is that negative 40,000 kilojoules per minute. And the Q in is 0. This one is negative. And from the combination of the equations, we see that work in should be 0 from combination. You can see it is the negative 40,000 should be equal to that negative something plus something. Therefore, work out term should remain here. That will be that 37 kilojoules per minute. You can see it is a very simple mathematical expression. This one is negative 40,000. You have negative sign here, 3,000 plus something that it makes 40,000, therefore this term is 0. And therefore here you will have the negative 37,000 kilojoules per minute. And when I say that negative, it should be work in. It's actually positive, it should be positive. Okay, work out is 37,000, work out is 37,000. It should be positive, so because when I say that work out, it is positive. Therefore, I will write the positive sign here. And then now comes the finish. We finish these processes. And when we say that, first let me ask if you have questions about, if you have questions till now. So input means negative. Yes, when we have the input, it means negative, but here it is out, it is positive. So I mean, I think you mean the work out. I have corrected it. No problem. If you have questions, you can ask. Otherwise, I will finish this example, and with this example, I will finish today's lecture for Thermodynamics 1. If you have questions, you can ask. Which one? 2 and 3, you don't understand. For the 2 and the 3, Q is positive. If it is positive Q, it means that it is in. You can see it here. Positive Q means it is in. Therefore, I just add the in, which is 20,000, positive. And the work is 0, therefore this term and that term is 0. Q out, there is no Q out, and therefore delta U will be 20,000. You just do this calculation for the 2 and the 3. Okay, it seems that nobody has the question, so therefore I will move on to the last part, which is 4 and the 1. With the 4 and the 1, I will finish the lecture. So if it is a cycle, so it is the property of the cycle. So if it is a cycle, for a cycle, delta U is 0. Change of internal energy is 0. Why it is 0? Because you have started from some point here, let's say that U1, and you go from that way, and you drop it, and you go that way, and you go this way. Anyway, you can go any direction. You come back to here, which is U1 is same as U2. Internal energy for the cycle is 0. But the work is not 0. Work 1, 2, it is not 0. Why it is not 0? Because say that this is the ladder, okay? So this one is ladder, and you are moving on that ladder to some height here. So you move up, and then you move back to down at the same point, okay? So you have 1, and then you go ladders up, and then come back again 2. So here your internal energy, sorry, that height doesn't change. H1 is same as H2, okay? Because you have moved upstairs and then downstairs. Height doesn't change, but you will do some work, which is not equal to 0. Okay, that is very clear because you should go up and then come back. Then the work should not be 0. Therefore, for the cycles, the work and the Q is not 0, but only internal energy is 0. So if it is 0, it means that these right-hand side terms, when you add them, it should be 0. So therefore, delta U total should be equal to delta U 1 to 2 plus delta U 2 and 3 plus delta U 3 and 4 plus delta U 4 and 1 should be equal to 0. Okay, for 1 to 2, it is the negative 2500. For the 2 and the 3, it is 20,000. For 3 and the 4, it is negative 40,000. And the 4 and the 1, it is for 4 and the 1, it is 0. So we should find it, and at the end, these sums should be equal to 0. So therefore, delta U 4 and 1 will be equal to, so let me do this, or you can do this calculation here. It is very simple calculation. So it will be that 22,500 kilojoules per minute. Okay, this is for 4 and 1. Delta U for 1, it is 22,500 kilojoules per minute. So let me add it here. So it will be 22,500 kilojoules per minute. And the question also says that the sum of all heat transfers is negative 200 kilojoules. It says that the sum of all heat transfers is negative 200 kilojoules. And the system completes 80 cycles per minute. This is also very important. Let's do that part. In 1 minute, you have 80 cycles. Okay, so if I go back to here, the sum of all heat transfers should be equal to negative 200 kilojoules. Therefore, I should convert these quantities into kilojoules. So for first one, which is Q12, it is 0 kilojoules. For Q23, it will be 20,000 kilojoules per minute. Okay, and I should convert this one into the cycles. In one cycle, how many? So in one cycle, how many kilojoules do we have? I should convert it into cycles, and therefore you will have that in 1 minute, you will have 80 cycles. Okay, if you do that, so you will have this term will cancel out, and you will have in one cycle 20,000 divided by 80. If you do this calculation, you will have 250 kilojoules for Q2 and the 3. Q3 and the 4, let's go back to this one. It is negative 3,000 kilojoules per minute. In 1 minute, I have 80 cycles. Therefore, it will be that negative 3,000 divided by 80. That one will be that 37.5 kilojoules. Okay. You see that I'm converting all of them per one cycle, because it says that sum of all heat transfers is negative. It is for one cycle. Now I will add them. So Q12 plus Q23 plus Q34 plus Q41 is negative 200. So for the first one, it is 0. For the second one, it is 250. For the third one, it is 37.5. This one is unknown. So therefore, you will have Q1 for 1 will be equal to Q41 will be equal to negative 200. So minus 250. So if there is any negative sign here, so that this one is negative. Actually, this one is negative, this one is negative. And then you will have the 250. The second one is negative. So 400 negative, again 412.5 kilojoules. Again, negative sign means that it is Q, let me go back to here, Q in. Again, negative sign, sorry, Q out. Negative sign means Q out. This one is for one cycle. You can convert it into minutes. It is also possible. So I have found it for the Q41, but it is for one cycle. I should convert it into 1 minute, so that Q41 will be equal to negative 4112.5 kilojoules per cycle, and in 1 minute I have 80 cycles, and therefore you will have this quantity, just multiply with the 80 and you will have 33,000 kilojoules per minute, again with a negative sign here. I just replace it back here, negative 33,000 kilojoules per minute. Okay, and you just apply. Let me see how many times do we have. We have run out of the time, so I will continue from this part for our next lecture. If you have questions, you can ask. Otherwise, I will stop it here.